Good day everyone, welcome to this organic chemistry tutorial where we are going to look at stereochemistry, and our main focus in this chapter will be isomerism. So before we can delve any further, let's try to understand what the term isomerism or what simply isomers are. Alright, so we're looking at isomers. Isomerism. So isomers are simply molecules that have the same molecular formula but they have different structural formula, or maybe the arrangement of atoms are different. So we are saying isomers are compounds with the same molecular formula but different structural formulae. So basically this is what we are talking about. They're simply molecules or compound rather with the same molecular formula but different structural formula. So now let's break these isomers or isomerism down. So I'm going to say isomers on top, or isomerism. So there are two major types of isomerism. We have what are known as stereoisomers and the other type we have are called constitutional isomers. So when you're talking about constitutional isomers, these are just the isomers that differ in the connection of the atoms in a certain compound. But when you're referring to stereoisomers, they are simply compounds that differ in the spatial arrangement of molecules. So that is the difference between constitutional isomers and also the stereoisomers. But these stereoisomers are further broken into two. So under stereoisomer, we have what are known as conformational So we have conformational stereoisomers and we also have what are known as configurational isomers. So when you're talking about conformational isomers, you are just referring to those isomers which are formed by just the rotation around a single bond, that is a single carbon to carbon bond. So those isomers which are formed by just the rotation of those atoms at that single carbon to carbon bond, they are referred to as conformational isomers. But when you are dealing with configurational isomers, you are simply referring to isomers that have a fixed spatial arrangement that cannot be interchanged or simply by rotating around a certain bond. So these ones they cannot be interchanged. Like, the arrangement cannot be interchanged by simply rotating around that bond. So those are known as configurational isomers. Then let's break down again the two types of configurational isomers. So when you're dealing with these configurational isomers, we're going to break them down again. Configurational. So configurational isomers. So for these configurational isomers, we have two types also. We have what are known as geometric and also what are called optic. So under this, we have also two types. So I'm going to break them down like this. We have what are known as geometric configuration isomers, and we also have what are known as optic configurational isomers, then or optical rather. So when you're talking about geometric isomers or geometric configuration isomers, these are further divided into two. So we have what are known as cis and trans. So we have what are known as cis and trans. Then we also have what are known as E or Z. So that is under geometric isomers. So I'll give an example of a cis. For example, we have a double bond there. Okay. We have a double bond, then we have a functional group, let's say, of an alcohol. Even this side, we have the functional group for a certain alcohol, like that. Then this side, we have a different chain attached, and also this side. So we can see that the functional group are on the same side of the double bond. Because these functional groups are on the same side, they are referred to as cis. But when you are talking about a situation whereby you have a double bond there, then one functional group, let's say for an alcohol, one is there and the other one is on this side, then we have something like that molecule. So for this one, since the functional group are on the opposite side of this double bond, this one is referred to as trans. So this is the difference. So trans, opposite functional group, but with cis we are referring to the functional group which are on the same side. But when it comes to E and Z, okay, so under E and Z, it is just similar to cis, but the difference here is that for E and Z, this letter E, it is just a German term. So it means that E was just gotten from a certain word in German which means entgegen. Okay, entgegen. So that's where this letter E was gotten. Entgegen, which just means opposite. Then this Z was gotten, it's also a German term which means Zusammen, or Zusammen, should I say. Zusammen, and this Zusammen, it is a German term which means that same side. So just like we talked about the cis and trans, for E, we'll have the group, different functional group, but if they're on the same side, it will be called the Z geometric configuration isomer. But when they are on the opposite side, it will be called the E configuration. Okay, let's try to look at some examples. So what I mean by E is whereby you have a double bond. Then on one side, we have, let's say, a functional group, which is for an alcohol. Then on the other side, the opposite side, we have, let's say, a functional group for we can use for a carboxylic acid, like that. Then we have a structure of that kind. So you can see that for this one, we're dealing with a different functional group, but when we're discussing the cis and trans, we're dealing with the same functional group. So since the different functional group are on the different or the opposite side, this is called E configuration. Or we can say antigen configuration, which is antigen geometric configuration isomerism. But when you are dealing with a certain scenario whereby you have the functional group like that on the same side, then this can be referred to as a Z configuration or Zusammen configuration, because you can see that the functional group are on the same side, but for this one, the functional group are on the opposite side for E. Okay, so that's one thing we are supposed to understand. All right, so with that understanding on the geometric, let's now talk about optical configuration isomers. Okay, so for optical configuration isomers, they're also divided into, we have what are known as diastereomers. So we have diastereomers and also what are known as enantiomers. So we have diastereomers and also what are known as enantiomers. So let's look at what these two terms what they mean. So when you're talking about okay, so we can start with the term for enantiomers. So when you're talking about enantiomers, you're just referring to the stereoisomers that are non-superimposable mirror images of each other. So that is for enantiomers. There are stereoisomers that are non-superimposable mirror images of each other. So, but when you're talking about the diastereomers, we are talking about those stereoisomers that are not mirror images of each other. Okay, so we've said for enantiomers, these are superimposable mirror images. So we're going to say these are superimposable mirror images of each other. That is for enantiomers. They are non-superimposable mirror images of each other, but for diastereomers, these are stereoisomers that are non mirror images of each other. So for this one, enantiomers, the mirror images, but for diastereomers, they are non-mirror images of each other. So basically, that is the difference between the diastereomers and also the enantiomers. So enantiomers mirror images. So for enantiomers, when we have something like ARA, we'll look at this configuration, then SS. These are, we can say that these two are enantiomers. If you have a certain molecule with ARA configuration, the other one has SS, we call them enantiomers. But with diastereomers, they just differ at one point. So we can have, for diastereomers, we can have something like one molecule has ARA, then the other one has RS. Okay, or it could be a situation whereby the one molecule has SS, then the other one has SR. Okay, so it could be SS, then other one has SR, like that. So we call them as diastereomers because they are just differing at one point. So in this case, we have SS and they just differ at R, and we have RR, but they just differ at S. So that is the meaning we must get from there. All right, so we have eluded what we need to appreciate. Now let's look at questions. So we're going to get questions from the tutorial sheet 1 and also others from the exam past papers. So let's start from we'll start with tutorial sheet 1. The first question was determine whether, so these will be our examples. Tutorial sheet 1, tutorial sheet 1, CHE 2105, on this part of isomerism. So the question was determine whether these molecules or these compounds or structures are diastereomers or enantiomers or conformational isomers. Same isomers, same molecule rather, or not isomers. So this was the question we are asked. So we are determining whether the two structures we are given, whether they are isomers, whether they are diastereomers rather, enantiomers, conformational isomers, constitutional molecule isomers rather, same molecule or not isomers at all. So let's start with the first one. So the first one we've been given, we have a Newman projection. So we have CH3, then with hydrogens like that. So we have a staggered configuration of that kind. This is a Newman projection which is known as staggered. Then we also have a source, okay, so this is a source, it's called the source. Then this is a staggered configuration, which is a Newman projection. Okay, let's look at these two structures. So we are determining whether they are diastereomers, they are conformational isomers, same molecule, or not isomers at all. So if we look at this structure, okay, so we have a methyl group there. Even this side we have a methyl group. So they're about, in fact, here it has to be a methyl. Okay, so from our understanding, from the first part where we started, we said that when you are dealing with these molecules, I should have mentioned to say when you have no chirality, whereby a carbon is bonded to 4 different things, we don't consider diastereomers or enantiomers. Okay, so in this case, we can say that this carbon there is bonded to is not chiral. In short, it is a chiral, so it is bonded to two things which are similar, which are hydrogens, so it is not chiral. If it is chiral, it means that this carbon will be bonded to 4 different things. For example, I can have a carbon bonded to a methyl, then this same carbon bonded to an halogen, let's say a bromine, like that. This same carbon bonded to an ethyl group, then this same carbon bonded to a hydrogen. So you say that this carbon is chiral because it is bonded to 4 different things, which are ethyl group, bromine, methyl group, and also hydrogen. So here, if we see these all these carbons we have, they are not chiral. Okay, and if we understood from the first part, we said that since these molecules, there is just that spatial arrangement in the way the atoms are arranged. So we can say that this can't be diastereomers, this can't be enantiomers. This is simply a spatial arrangement of molecules. These differ by a spatial arrangement of molecules, and therefore they will be called conformational isomers, because we can just see that these atoms, in this case, they are arranged in staggered Newman projection, but in this case, they are just arranged in sawhorse projection. So there's just that difference in the spatial arrangement of these molecules, and for that reason, they are known as conformational isomers. So we say conformational isomers. All right, let's look at the second one. So for the second one, we have this structure. Chlorine there, then we have a hydrogen, we have a methyl, we have another methyl like that, then we have another structure which is like this. So we have a hydrogen this side, we have a chlorine this side, then on top we have a methyl CH3, then down here we have a methyl like that, we have a hydrogen, then we have a chlorine. Okay, so let's look at this structure, these two structures which we have here. Okay, so we have this structure and also this one here. Okay, so for this one, you can see that the carbons are bonded to 4 different groups. So here, these carbons are chiral. And because they are chiral, we need now to determine whether it is R configuration or S configuration. So one thing you must understand is that for R configuration is clockwise. Okay? So if you're moving in the clockwise manner, it is R. Then for S configuration is anti-clockwise. So S will be anti-clockwise like that. And the other thing we must understand here is that when determining, you must just need to consider the carbon you are talking about, then you look at the groups which carbon is attached to. So let's determine whether it is R or S on the first structure we've been given. So we consider this carbon which is here. So this carbon is bonded to a chlorine molecule, hydrogen, and also a methyl. So let's determine whether it is R or S. So we're going to assign 1 to the group which is larger than the other. So in this case, you consider the atoms which are directly linked to this carbon and not like as such like the entire molecule. Okay, so if we consider the atomic mass, the one which has the highest, it is this chlorine. So we're going to assign 1 on chlorine, then we'll assign 2 to this group here. Okay, so in this case, we are just considering the entire group as such. So this group will be 2, then 3 will be a methyl there, then 4 will be that group there. Okay, so we are moving in this manner. So 1, we are starting on chlorine like that. Then, okay, let me use a different ink. Okay, so we are starting on 1, then we move to 2, then 3. So we can see that this kind of movement is actually a clockwise movement. Then the 4th group, which is hydrogen, as we can see, it is towards us. So if you draw this Fisher projection, then you are referring to this. So these which are horizontal, the horizontal lines, meaning that they are pointing towards the observer. So horizontal lines, it's towards you as an observer. Then these vertical lines, they simply mean away from you as an observer. Okay, so that is one thing we must appreciate there. So because this hydrogen is pointing away, towards you, it means that it is in front. Then if it was pointing away from you, it means that it is behind. And because this hydrogen which is pointing towards you, which is in front, and it's a fourth group, meaning that we need to interchange the configuration. So always interchange the configuration if the fourth group is in front or it is pointing towards you. So it was initially our configuration, so we're going to change it to S configuration. So that is what we need to do there. So that is S. Okay, so that is actually S. Then now let's look at the other carbon there. So for the first one, we will determine that is S. So we look at this one. This one also we assign one to chlorine. Then the entire group we assign it to this group here will be 2. Then 3 will be this group. So we are moving in this manner, and this kind of movement is actually anti-clockwise. Okay, it is anti-clockwise, so it should be S. Now let's look at the fourth group, which is hydrogen. The fourth group is pointing towards you, so it is in front. Because it is in front, we need to interchange the configuration from S to R. So it is from S to R. So we'll now assign it to be R. So this will be R. So here we have S. We have SR. Let's look at the other one. So for this one, as we said, if you have a wedge, I should have mentioned that whenever you have a wedge, something like this, a wedge simply means that the group is in front. Okay, then if you have a dash means that the group is behind. So we're going to be using the same analog even to contemplate these questions here. Alright, so we have a carbon there. Let's look at the configuration. So we have 1, the chlorine, then this entire group will be 2, then the methyl will be 3. So 1, then the entire group 2, then 3. So we're moving like this. So this kind of movement is clockwise, but the fourth group, which is hydrogen, it is in front. For that reason, we must interchange the configuration from R, which is clockwise, to S, which is anti-clockwise. So that will be S configuration. So we have S there. Then we come to the other carbon, which is there. So this carbon, we're also going to count 1. Then this entire group will now be 2. Then we'll have 3. Then the fourth group is hydrogen. So in this case, we are moving like this. This is anti-clockwise movement. And because the fourth group, which is hydrogen, it is in front, we're going to interchange the configuration from S to R. So it will be now R configuration. So we must now write R configuration there. So this side we have S R. This side we have SR. Then this side we also have SR. Okay. So we have SR. So let's just now be able to determine the configurations. Okay. Let's now determine the configurations. So you can see that we have SR, but this side we have SR, even this side we have SR. Okay, let's just go through one more time. So 1, 2, 3. So 1, 2, 3, we are moving like that. Okay, this is we're moving like that. That is anti-clockwise. So we're going to change it to R, which is clockwise. Then there it was 1, 2, so we're moving like that. This was R, we interchanged it to S. So yes, we are right. Then here, yes, this is correct. 1, 2, 3. So we are moving like that. This is R, but we interchange it to S. Then 1, 2, we are moving like that. This is anti-clockwise, but we interchange it to clockwise. Yes. So basically, this is what we have. We have SR. Then we have SR and SR. So what can we comment about this kind of isomerism? So we said, just to remind ourselves, if we have something like R, then RS, the one which just differ at one point, we call them diastereomers. Okay, so if we have this, we said they are diastereomers. Then if we have the opposite configuration, let's say there is R, then everything has now changed to SR. If you have mirror images, we said the configuration, this should be S. If you have something like this, RR, then changes to SS, or maybe you had SS, then changes to RR. So in this case, we said that for this one, it means that those compounds are enantiomers because they are mirror images of each other. Or in a case whereby you have RS, then you have SR like that. So even in this case, they are simply enantiomers because they are mirror images of each other. But let's look at our scenario. Let's look at this scenario. So for this one, we had SR, we have SR and also SR. So we can see that there's no mirror, they are not mirror images of each other. It is just the same compound which is written in a different configuration. So this is just the same compound. Okay, let's look at the other one. So this will be question part 3. Okay, let's take one from a past paper. So let's take the question we are asked in 2023 exam. So in 2023 exam, there is this question that is CHE 2105. There was this question which is like this. CH3 there, HH, then we have HBr, CH3. Then this other one, we have CH3, HBr, HCH3. So we are still determining the type of isomerism which exists between these two compounds. So we can see that okay, so we can start from this carbon here. This carbon, there's no chirality because there are two hydrogens attached to it, unless all the groups which are attached to this carbon were different. But you can see that the bottom carbon, there is chirality because we're going to consider this group to be different. Then this hydrogen bromide and the methyl also to be different. So since we have now understood how to be determining, so we are going to determine our configuration, which is there. So you can see that this will be 1, then this entire group will be 2, then the methyl will be 3. So we're going to move in this manner, and movement in this manner, it is actually anti-clockwise movement. So since it is anti-clockwise, but we can see that the fourth group, which is hydrogen, it is in front, and because it is in front, we are going to change the configuration from S to R. So that is R here. Then let's look at this one also. So this carbon there's no chirality because it has 2 hydrogen attached. Let's look at the bottom carbon. So this one, there's chirality because we have bromine, hydrogen, methyl, and this group, which is different, an ethyl group. Okay, so let's now determine the configuration here. So we're going to say 1, then this group will be 2, then the methyl will be 3. So we're going to move like this. The movement in this manner, it is actually clockwise movement, and because the hydrogen, which is the fourth group, it is in front, we're going to change from R, which is clockwise, to anti-clockwise, which is S. So you can see that we're going to have an S configuration. Okay, because we have a mirror image, the mirror image of R, which is giving us S. So here there is mirror image of the mirror images of each other, and for that reason, these are enantiomers. So for enantiomers, we said they are mirror images of each other. So these are simply enantiomers. Alright, let's look at another question from this 2023 exam. Okay, so 2023 exam, that was the first part, that is question number 2. Okay, so we have these molecules. So we have a bromine there, then it's attached to a methyl, then also a hydrogen there. Then the other group we have, it is in a staggered von Neumann projection. So we have hydrogen there, then we have a Br bromine, then we have another hydrogen, then we have an ethyl group there, CH2, CH3, then we have H, then we have HSO. Okay, so let's look at these two structures. So we'll start with the first structure. So here, yes, there is some form of chirality, but it won't be able to be comparing these two. So we can't compare this structure with this, because these two structures, as they have drawn here, we have chirality on the one carbon, but here there's no chirality, because you can see that one carbon is bonded to 2 hydrogen, and also in this case to 2 hydrogens. So the other thing we must consider is just to check, is this compound the same or not? So we have a Br there. Okay, let me use a different ink. So we have a Br, the same Br which is there. Then we have this ethyl group, which is here, that is because this one has a hydrogen there and also another hydrogen, then it has a CH3 at the end. So this is an ethyl group, which is just the same as that ethyl group there. Then we have how many hydrogen? So here there is a methyl CH3. So if you count the number of hydrogen remaining now, 3 plus 1, they are 4. So there are these hydrogen 1, 2, 3, 4. So you can see that this is actually the same molecule, but it is just drawn with different connectivity. There is just a difference in the way these atoms are connected. And we said isomerism, which have different connectivity or connection, that is just the constitutional isomerism. So they are constitutional isomers. Okay, so that is what we need to understand. All right, so this is where we end. Okay, so this is where we end with the isomerism. Thank you for watching and have a great day. So don't forget to subscribe. Don't forget to like, subscribe. Okay, don't forget to like, share, and also subscribe. Then for more tutorial videos, study materials, past papers, quizzes, you can subscribe to this channel. And also we have Meticulous Study Hub. This is a platform where you find all these tutorial sheets, tutorial videos, study materials, past papers, quizzes. They are already available on our app, Meticulous Study Hub app, and also on our website. So we find A-level natural sciences, NS, and also for second year data videos, and also if you want videos in biochemistry, physiology, anatomy, immunology, and these other courses. We even have a junior section, and also for senior section, videos, study materials are already available. So you can contact us using this number or just via an email. So thank you for watching.